You know that feeling when you think you know someone really well, and then they do something so completely unexpected, so totally out of left field, that you have to stop and fundamentally rethink everything you thought you understood about them? Like, you built this entire mental model of who this person is, and then in one moment that model just collapses and you realise you never actually knew them at all? That's Neptune. Because on the surface, well, not literally on the surface, there is no surface, but you get the idea, Neptune looks like it should be the boring one. It's the last planet in our solar system. It's tiny compared to Jupiter and Saturn. It's so far away that even with a decent backyard telescope you can barely make it out as anything more than a faint bluish smudge. It gets almost no sunlight. It's cold beyond comprehension. It's the planet that nobody names their kids after, nobody makes documentaries about, nobody puts on their list of top 10 most interesting places in the solar system. It's basically the quiet kid sitting in the very back of the classroom, the one nobody ever talks to, the one who gets completely overlooked at every single social event, who fades into the background while louder, flashier personalities like Jupiter and Saturn take all the attention. But here's the thing about that quiet kid in the back of the classroom. Sometimes, the quiet ones are the most interesting. Sometimes when you actually sit down and pay attention to them, when you stop being distracted by Jupiter's great red spot and Saturn's photogenic rings, and you actually look at what Neptune has going on, you realise you've been ignoring something extraordinary this whole time. Neptune is not boring. Neptune is not quiet. Neptune is, without any exaggeration whatsoever, one of the most violent, bizarre, chaotic, and scientifically baffling places in the entire solar system. We're talking about a planet where winds routinely blow faster than the speed of sound, not during storms, just as a normal Tuesday, where storms the size of entire planets appear fully formed in the atmosphere and then completely vanish, leaving no trace, for absolutely no reason that our models can fully explain, where the interior might be filled with an ocean of exotic matter that simply doesn't exist anywhere else we can access in the universe, matter in states of such extreme pressure and temperature that our best laboratories can barely scratch the surface of recreating them, where diamonds might literally be raining through the sky right now as you watch this video, where a single year lasts longer than all of recorded human civilization combined, and where the largest moon in the system orbits backward in the completely wrong direction, something so fundamentally, cosmically strange that scientists have been arguing about how it possibly happened since the moment it was discovered. And yet, despite all of this, despite being arguably the most extreme and the most scientifically fascinating planet in our entire solar system, Neptune has only ever been visited by one spacecraft. One. In all of human history, in 70 years of the space age. One spacecraft. And that visit, that single, brief, unrepeatable close encounter, lasted only a matter of hours before the spacecraft flew on into interstellar space and Neptune was left alone again. One visit, a few hours, and then nothing. We have spent more collective time as a species arguing about whether a hot dog is a sandwich than we have spent flying a spacecraft past the most extreme planet in the solar system. Let that sink in for a moment. So today, we're going to do something about that. We're going to go deep on Neptune, deeper than any spacecraft has in 35 years. We're going to talk about its discovery, which is genuinely one of the most dramatic stories in the history of science. We're going to talk about its weather, which makes every hurricane you have ever worried about look like a light breeze. We're going to talk about its magnetic field, which violates basically everything we thought we knew about how planetary magnetic fields work. We're going to talk about its interior, where diamonds may be falling through exotic oceans right now. We're going to talk about its rings, which nobody ever mentions even though they're fascinating. And we're going to talk about its moons, particularly one moon that is so bizarre, so geologically active, so cosmically out of place, that it might be one of the most important objects in the outer solar system for the future of astrobiology. And through all of it, we are going to confront the uncomfortable reality that we know almost nothing about this planet, not because it's not worth studying, but because we haven't tried hard enough. Because Neptune has been sitting out there for 4.5 billion years, doing extraordinary things, generating mysteries that our best scientists genuinely cannot solve, and we have sent exactly one spacecraft to take a look and then moved on. That changes today, metaphorically at least. Let's go. Chapter 1. the planet that was found with pure mathematics. Let's start at the very beginning. Because the story of how Neptune was discovered is not just a good story, it is one of the greatest stories in the entire history of human knowledge. It is a story about the power of mathematics to reveal hidden truths about the physical universe. It is a story about ambition and patience and institutional failure and international rivalry. And it is a story that, even today, more than 175 years later, still has people arguing about who deserves the credit. It starts not with Neptune, but with Uranus. It is 1781. A man named William Herschel, a German-born musician who had emigrated to England and taught himself astronomy, built his own telescopes, and spent his evenings systematically mapping the sky, is observing from his garden in Bath. He notices something, an object in the eyepiece of his telescope that looks slightly different from the stars around it. It's a touch fuzzy around the edges. When he looks the next night, it has moved against the background stars. Stars don't do that. This is something else entirely. William Herschel has just discovered Uranus, the first new planet to be found in all of recorded human history. Not a planet known since antiquity, not a planet described in ancient texts, not a planet that anyone had ever deliberately searched for. A genuinely new planet, found by systematic observation with a telescope. For the first time in history, someone had pushed the boundary of the known solar system outward. The discovery of Uranus caused an enormous sensation in the scientific world, as you'd expect. And in the years following its discovery, astronomers immediately started doing what astronomers do. They began carefully, meticulously tracking Uranus's orbit, plotting its position night after night, month after month, year after year, calculating exactly where it should be at any given moment based on Newton's laws of gravitation, and then checking whether it was actually there. For a while, the agreement was good. Uranus was behaving itself, following its predicted path through space, confirming that Newton's laws applied even to this newly discovered distant world. Everything looked fine, and then, gradually it didn't. By the 1820s and 1830s, a problem had become impossible to ignore. Uranus was not where it was supposed to be. Not by some tiny, ambiguous amount that might be explained away as measurement error or an imprecision in the initial calculations. By a real, substantial, systematically growing amount. The planet was consistently drifting away from its predicted position. And when astronomers went back and looked at historical records, because it turned out that Uranus had actually been observed multiple times before Herschel's discovery, just mistaken for a star, the problem got even worse. The historical observations simply could not be reconciled with the modern ones using any straightforward application of Newton's laws. Uranus was misbehaving, and the scientific community needed to figure out why. At this point, there were essentially two categories of explanation available. The first was that Newton was wrong, that the law of universal gravitation, the equation that had successfully described the motion of everything from apples falling from trees to the orbits of planets around the sun, broke down at very large distances or very weak gravitational fields. This was not a popular idea, to put it mildly, because Newton's laws had accumulated such an enormous body of successful predictions over the previous 150 years that doubting them felt, to most scientists, like doubting arithmetic itself. But it was a logical possibility. The second explanation was that there was something out there, something beyond Uranus, something too faint and too distant to have been detected yet, that was exerting a gravitational pull on Uranus and tugging it away from its expected path, an unseen planet, a gravitational ghost, leaving its fingerprints in the orbital data without ever being directly observed. The scientific community overwhelmingly favoured the second explanation, and two mathematicians, working completely independently, knowing nothing of each other's work, separated by the English Channel and a significant linguistic barrier, decided to find that unseen planet using nothing but the data and their mathematical skills. The first was John Couch Adams. Adams was a young Englishman, a student at Cambridge who was considered among the most brilliant mathematicians of his generation. He began working on the Neptune problem in 1843, still a student, motivated by the sheer intellectual audacity of the challenge. His approach was inverse problem solving at its most ambitious. Take the observed deviations, the precise, carefully measured ways in which Uranus's actual position differed from its predicted position, and work backwards. If there is a hidden planet somewhere beyond Uranus, then that planet must be at a specific distance, moving at a specific speed, currently located in a specific part of the sky in order to produce exactly those deviations. The deviations in Uranus's orbit are not random noise. They are information. They are a message from the hidden planet, encoded in the orbital mechanics of its neighbour, and if you're skilled enough and patient enough, you can decode that message. Adams worked on this problem with extraordinary focus and discipline, and by September 1845 he had a solution, a prediction, a location in the sky where he believed a new planet would be found. He sent his results to James Challis, the director of the Cambridge Observatory, and asked that a search be conducted. Challis forwarded the prediction to George Biddle Airy, the Astronomer Royal, the most senior astronomer in Britain, the man with the authority to direct a serious telescopic search. Airy received Adams's prediction. He read it. He had some questions and doubts. He sent a letter to Adams asking for a clarification on a specific point about the theory. Adams, for reasons that are somewhat murky, perhaps he was busy, perhaps he was intimidated, perhaps he simply didn't understand the urgency, didn't respond promptly. And Airy extraordinarily did essentially nothing with what Adams had given him. He did not initiate an immediate search. He continued with his other duties. The prediction sat. Months passed. Meanwhile, in France, Urbain Le Verrier had independently arrived at the same problem. Le Verrier was a mathematical astronomer of formidable talent and considerable ambition, working at the Paris Observatory. He too had looked at the anomalies in Uranus's orbit. He too had decided to solve the inverse problem and find the hidden planet mathematically. And through 1845 and into 1846, he published a series of increasingly refined papers, each one narrowing down his prediction of the unknown planet's location with greater and greater precision. In June of 1846, Le Verrier published a prediction that placed the unknown planet at a specific location in the constellation Aquarius. Airy read this paper, and suddenly, embarrassingly, realized that Le Verrier's predicted position was almost identical to the position Adams had given him nearly a year earlier. Two mathematicians, working completely independently on opposite sides of the channel, had pointed their mathematical fingers at the same spot in the sky. At this point, Airy finally panicked into action. He arranged for the Cambridge Observatory to begin a search using Adams' predictions. James Challis started looking in late July of 1846, but the search was slow and somewhat disorganized. Challis was comparing his observations to a star catalogue to identify anything that didn't belong, and this process was tedious. He was actually observing Neptune on multiple occasions in August without recognizing it, because he wasn't processing his data quickly enough. Meanwhile, Le Verrier had sent his most precise prediction to Johann Galle at the Berlin Observatory, specifically requesting that Galle conduct a search. Galle received the letter on September 23, 1846. He got permission from the observatory director that same evening, pointed the Berlin refractor at the location Le Verrier had specified, and compared what he saw to a new star chart that had just been completed for that region of sky. Within an hour, he had found an object that was not on the chart. It was within 1 degree of where Le Verrier's mathematics had said it would be. Neptune had been found, on the very first night of a dedicated search using Le Verrier's prediction. When news reached England, the British scientific establishment found itself in an acutely uncomfortable position. The French had discovered a new planet, the most celebrated scientific achievement in decades, using mathematical methods that a British mathematician had also independently developed a year earlier, and which the British astronomical establishment had completely failed to act on. The embarrassment was enormous. What followed was one of the most contentious priority disputes in the history of astronomy. British scientists scrambled to establish Adams's claim to co-discovery. They published his calculations. Airy wrote defensive justifications of his behaviour that were not entirely convincing. The French, understandably, were furious at what they saw as a retroactive attempt by the British establishment to steal credit for a discovery they had failed to make. Scientific societies on both sides of the channel published competing accounts of the story. The dispute played out in academic journals, in newspapers, and in diplomatic back channels. It became genuinely international. The historical consensus that has emerged over the subsequent 175 years is roughly as follows. Le Verrier deserves primary credit for the discovery, because it was his prediction that was actually followed up, and it was his letter to Gal that resulted in Neptune being found. Adams deserves substantial credit for independently solving the same mathematical problem and arriving at essentially the same answer, which powerfully confirmed that the prediction was not a lucky guess, but a genuine mathematical result. Galle and his assistant Heinrich Louis de Rest deserve credit for the actual work of identifying Neptune in the telescope, and Airy deserves the historical legacy of being the man who had the prediction in his hands and didn't act on it. A cautionary tale about institutional inertia that planetary scientists still cite to this day. But here is the thing I want you to take away from all of this political drama, the thing that matters most. Strip away the nationalism and the wounded pride and the dispute over who gets whose name in which textbook. What actually happened here is one of the most remarkable demonstrations of the power of human reasoning in history. Two people, working independently, using only mathematics, using only pencil and paper and the observed wobble of a distant planet, reached their minds across 4.5 billion kilometers of empty space and put their fingers on an object they had never seen, could not see with the naked eye, had no direct observational evidence for. And they were right. They were right to within 1 degree. This was proof, undeniable and spectacular proof, that the universe actually follows rules. Consistent, discoverable, mathematical rules that hold true not just here on Earth, not just in the nearby solar system, but out there at the very edge of the known planets. It was proof that human reason, properly applied, can reach places that human eyes cannot. It was a validation of the scientific enterprise on a scale that had no precedent. Neptune was the gift that mathematics gave to astronomy. And from the very first moment it was found, it started being strange. The first thing astronomers noticed, even through modest 19th century telescopes, was that distinctive deep blue colour. Not just blue the way Uranus is blue, more intensely, more vividly blue, an electric, almost unsettling blue that immediately suggested a different atmospheric composition. The second thing they noticed was that it had a moon, found just 17 days after the planet itself by the British astronomer William Lassell, and this moon, named Triton, was orbiting Neptune in exactly the wrong direction. Backwards, retrograde, going around the planet in the opposite sense to Neptune's own rotation, which was and remains profoundly strange. We will come back to Triton later in this video, and I promise you it is worth the wait. But before we get to moons, before we get to rings, before we get to magnetic fields, we need to understand what Neptune fundamentally is, because the answer to that question is more complicated and more scientifically contested than most people realise. Chapter 2. What Neptune actually is. And why the answer is stranger than you'd think. Okay, let's do some fundamentals, but let's not make them boring, because Neptune's fundamentals are genuinely not boring. Neptune is the 8th planet from the Sun, and at an average distance of approximately 4.495 billion kilometers, it is the most distant planet in our solar system. Light, travelling at 300,000 kilometers per second, takes about 4 hours to make the journey from the Sun to Neptune. When you look at Neptune through a telescope, you're not seeing it as it is right now. You're seeing it as it was 4 hours ago, because that's how long its light has taken to reach you. The Sun, from Neptune's perspective, is not the enormous blazing disk that we experience here on Earth. It is a very bright point of light. Brilliant, certainly, brighter than any star in our night sky from Neptune's viewpoint, but just a point, a star, not something you feel warming your skin. As a result, Neptune receives approximately 900 times less solar energy per square meter than Earth does. It is cold in a way that is genuinely difficult to conceptualize. Cloud top temperatures of around negative 200 degrees Celsius, or about 72 Kelvin. The kind of cold where almost every gas we breathe becomes liquid or solid. Neptune's diameter is approximately 49,500 kilometers, about 3.88 times the diameter of Earth. You could fit roughly 58 Earths inside Neptune's volume. It is the 4th largest planet in the solar system by diameter, behind Jupiter, Saturn and Uranus. But here is something interesting. Despite being slightly smaller in diameter than Uranus, Uranus's diameter is about 51,100 kilometers, making it modestly wider. Neptune is actually significantly more massive. Neptune has a mass of about 17.15 Earth masses. Uranus comes in at about 14.54 Earth masses. Neptune is both smaller and heavier, which means it is denser. And in planetary science, density is information. Density tells you something about what a planet is made of, how it is structured internally, how it formed. Neptune is classified as an ice giant, the same category as Uranus, and a fundamentally different category from Jupiter and Saturn, which are gas giants. This is not just a label. The distinction reflects a real and profound difference in composition and internal structure. When planetary scientists use the word ice in this context, they don't mean what you put in your drink. They are using a technical definition that refers to volatile compounds, primarily water, methane, and ammonia, that exist in the extreme high-pressure, high-temperature conditions of a planetary interior in states of matter that have no good everyday analogy. Under the conditions found deep inside Neptune, water, methane, and ammonia are neither solid nor liquid nor gas in any conventional sense. They are in exotic high-pressure fluid states that are simultaneously denser than typical liquids, more mobile than solids, and electrically conducting in ways that normal fluids at normal conditions are not. The word ice is essentially a historical holdover from when we first categorized these compounds. It doesn't mean frozen. These exotic ices are the dominant component of Neptune's interior, and understanding them is the key to understanding what Neptune actually is. The interior of Neptune is thought to be organized into roughly 3 main regions. At the outside there is the atmosphere, the region we can actually observe directly with telescopes. This consists primarily of molecular hydrogen and helium, similar in composition to the outer layers of the gas giants Jupiter and Saturn, but with an important addition: methane. Neptune's atmosphere contains about 1.5% methane by volume, and that methane is absolutely crucial for explaining Neptune's most visually striking feature. Methane is a very efficient absorber of red and orange wavelengths of light, and it scatters and reflects blue and violet wavelengths preferentially. This is why Neptune appears such a deep, vivid, electric blue. When sunlight enters Neptune's atmosphere, the methane strips out the warm colours and bounces back the cold blues. The result is that extraordinary colour that caught the attention of 19th century astronomers even through primitive telescopes. Uranus also has methane in its atmosphere, at roughly similar concentrations. Yet Uranus appears a much paler, more washed out blue-green, while Neptune is a deep, saturated, almost jewel-like blue. This difference in colour between the two planets, despite similar methane abundances, is actually not fully explained by current models. One hypothesis is that Neptune's atmosphere contains an additional unknown absorbing compound, something that is present in Neptune but not in Uranus, or present in different concentrations, that is contributing to the extra blue saturation. Some researchers have suggested it could be a photochemical haze compound, a product of methane being broken apart by ultraviolet sunlight and then reforming into more complex hydrocarbons. But the specific compound, if it exists, has not been definitively identified. Even Neptune's colour, the first thing anyone notices about it, is partly a mystery. Beneath the observable atmosphere, the second and by far the largest region of Neptune is the mantle, a vast deep region of those exotic high-pressure ices. This mantle constitutes roughly 80% of Neptune's total mass. It is the planet, in the sense that most of what Neptune is, by mass, is this strange interior region. The pressure in the mantle increases from essentially zero at the atmosphere-mantle boundary to millions of times Earth's sea level atmospheric pressure at the deepest levels. The temperature increases from the very cold temperatures of the cloud tops to potentially tens of thousands of Kelvin in the deepest parts of the mantle, hotter than the surface of the Sun, even though Neptune's surface is among the coldest places in the solar system. This is not a contradiction. The heat is coming from inside, not outside. The interior of Neptune is extremely hot. The surface is extremely cold because that's where the heat escapes into space. In this mantle region, under those extreme conditions, the behaviour of water, methane and ammonia becomes deeply strange. Water molecules, subjected to pressures of millions of atmospheres and temperatures of thousands of Kelvin, enter what physicists call a supersonic state, a phase of matter where the oxygen atoms form a rigid crystalline lattice, like a solid, but the hydrogen protons, stripped from their oxygen partners by the extreme thermal energy, flow freely through that lattice like a liquid or like an electrical current. It is simultaneously solid and liquid. It has no good everyday analogy. It is a state of matter that simply does not exist naturally anywhere on Earth's surface. Meanwhile, the methane in the mantle is undergoing something even more dramatic. The extreme pressure and temperature are sufficient to break the molecular bonds of methane, the bonds between carbon and hydrogen, releasing free carbon atoms into the high-pressure interior fluid. And those carbon atoms, now free and under millions of atmospheres of pressure, do what carbon does under extreme pressure. They form diamond. This is the diamond rain hypothesis, and it is one of the most evocative and discussed ideas in modern planetary science. The proposal, based on theoretical models and increasingly on laboratory experiments, is that deep inside Neptune, carbon atoms liberated from methane are crystallizing into diamond under the extreme pressure, forming solid diamond particles that then, because diamond is denser than the surrounding fluid, sink downward through the mantle like raindrops falling through air. Diamond precipitation, an ongoing continuous process of diamonds forming and falling through the interior of the planet, and not small diamonds, not microscopic crystal grains. Some models suggest that the diamond particles could grow to substantial sizes as they fall, accumulating mass as they sweep up more carbon on their way down, potentially reaching the size of golf balls, or oranges, or basketballs. And at the very bottom of the mantle, where the pressure is greatest and the diamonds can fall no further, there may be a vast accumulation, a diamond ocean in liquid form at those pressures, or perhaps a solid diamond layer that has been building up over 4.5 billion years of diamond precipitation. Now, I want to be precise about what we actually know here, because this idea sometimes gets presented with more certainty than is justified. We have never directly sampled Neptune's interior. No probe has ever gone into Neptune. The closest we've come is Voyager 2's flyby at a distance of about 4,950 kilometers from the cloud tops in 1989, and even that gave us only atmospheric data. The diamond rain hypothesis is based on theoretical models of high-pressure carbon chemistry and on laboratory experiments, particularly experiments using high-powered laser facilities to generate shock waves that briefly recreate the pressure and temperature conditions thought to exist in Neptune's mantle. In those experiments, scientists have found evidence that diamond does form under these conditions. The experiments have gotten increasingly sophisticated, and the evidence has gotten increasingly compelling over the past decade. But from laboratory evidence to it is definitely happening inside Neptune right now on an enormous scale is still a significant inferential leap. The models have uncertainties. The interior structure of Neptune is not perfectly known. The exact temperature and pressure profiles of the mantle, the exact composition, the exact thickness of various layers. These all have significant uncertainties that propagate into uncertainties about whether and how extensively diamond formation is occurring. What is not in doubt is that Neptune's interior is generating a substantial amount of its own heat. This is one of the most important and solidly established facts about Neptune. It radiates approximately 2.6 times more energy out into space than it receives from the Sun. For a planet so far from its star that it receives almost no solar energy in the first place, this is an extraordinary thing. Neptune is not just passively reflecting sunlight, it is actively pumping heat into space from some internal source. This internal heat source matters for everything else about Neptune. It matters for the atmospheric dynamics, which we're about to discuss. It matters for the interior structure. It may matter for the habitability of its moon Triton. Understanding where this heat comes from, and why Uranus, Neptune's structural twin in so many ways, has essentially no excess internal heat, is one of the most important open questions in planetary science. The leading explanation is primordial heat, thermal energy deposited during Neptune's violent formation 4.5 billion years ago, when the accretion of rocks, ice, and gas released enormous amounts of kinetic energy as heat, and that heat has been slowly leaking out ever since. But over 4.5 billion years, significant amounts of that initial heat should have escaped. So there are almost certainly additional contributing processes, gravitational differentiation, as denser materials continue to slowly settle toward the core, converting gravitational potential energy into heat, possibly ongoing chemical differentiation in the exotic ices of the mantle, possibly processes related to the supersonic phase transitions of water. We don't have a complete accounting of Neptune's energy budget, and the discrepancy between Neptune and Uranus, which should be similarly heated but isn't, is one of the genuine puzzles of outer solar system science. What we can say with certainty is this: Neptune has significant internal energy. That energy drives its atmosphere into extraordinary behaviour, and it is to that extraordinary atmospheric behaviour that we now turn. Chapter 3. Neptune's weather is genuinely violent beyond comprehension. I want you to stop for a moment and think about the most extreme weather event you have ever personally experienced. Maybe it was a Category 4 hurricane making landfall nearby. Maybe it was a severe tornado outbreak that shut down your region for days. Maybe it was a blizzard that buried your city under meters of snow and paralysed everything for a week. Maybe it was a derecho, or a supercell, or a haboob, or any of the other forms of spectacular atmospheric violence that Earth produces with some regularity. I want you to hold that memory. Really feel the sense of scale and power and danger that comes with that kind of weather. The wind that you can barely stand up in, the rain hitting like a physical force, the darkness at midday, the sense of nature completely overwhelming human structures and systems. Now I want you to understand that compared to Neptune, that weather event was essentially nothing. It was a mild, pleasant afternoon. It was the kind of weather that Neptunian meteorologists, if they existed, would classify as calm and uninteresting. On Neptune, the weather conditions you just imagined would not even be notable enough to put on a weather map. Neptune holds, without serious contest, the record for the fastest sustained winds in the solar system. The winds in Neptune's upper atmosphere, not in a storm system, not in some exceptional local event, but in the general circulation of the atmosphere, have been measured at up to 2,100 kilometers per hour. Let me put that in terms that connect to something you know. The speed of sound at sea level on Earth is approximately 343 meters per second, or about 1,235 kilometers per hour. Neptune's winds blow at roughly 580 meters per second. That is approximately 1.7 times the speed of sound. They are supersonic. Not barely supersonic, significantly, consistently supersonic. To put this in a different kind of context, the fastest wind speed ever reliably recorded on Earth's surface was about 408 kilometers per hour during a severe tropical cyclone in Australia. Neptune's baseline atmospheric wind speed is more than 5 times that record. Not Neptune's storms, not Neptune's exceptional weather events. The ordinary background wind, on an average day, at the cloud tops, is more than 5 times the most extreme wind speed ever measured anywhere on the surface of planet Earth. This is staggering, and it becomes even more staggering when you consider the context in which these winds exist. Neptune is the farthest planet from the Sun. It receives the least solar energy of any planet, about 900 times less per square meter than Earth, as we discussed earlier. If you think of solar energy as the driver of atmospheric dynamics, which is a reasonable first approximation, since on Earth and on most planetary bodies solar heating is the primary energy source for weather, then Neptune should have the least energetic, least active, slowest moving atmosphere of any planet. It is receiving almost nothing in the way of solar energy to power weather with. Jupiter, which is much closer to the Sun and has far more solar energy available, has wind speeds that max out at around 500 to 600 kilometers per hour in its strongest jet streams. Saturn, slightly further from the Sun, reaches about 1,800 kilometers per hour in some equatorial regions. Impressive, but still significantly below Neptune's speeds. Both of these planets have vastly more solar energy available than Neptune does. Neptune blows them both away, literally. The resolution to this paradox almost certainly lies in Neptune's internal heat source. The 2.6 times solar luminosity that Neptune is radiating from its interior represents a substantial energy source for driving atmospheric dynamics. As this internal heat rises toward the surface, it creates temperature gradients, warmer regions rising, cooler regions sinking. Temperature gradients drive pressure differences. Pressure differences drive winds. And apparently, in Neptune's specific atmospheric composition, at Neptune's specific temperature and density, with Neptune's specific rotation rate, this internal heat is extraordinarily efficient at generating high-speed winds. But the detailed mechanism, the specific chain of physical processes that takes you from Neptune has the internal heat to Neptune has supersonic winds at the cloud tops, is not fully understood. We don't have a self-consistent, validated atmospheric model that successfully predicts the magnitude of Neptune's wind speeds from first principles. This is an open problem in planetary atmospheric science. Neptune's storms are equally dramatic and equally baffling. The most famous is the Great Dark Spot, a massive storm system observed by Voyager 2 during its 1989 flyby. At the time of observation, the Great Dark Spot was approximately the size of the planet Earth, an entire Earth-sized anticyclonic vortex, a giant rotating storm spinning in the opposite direction from the surrounding atmospheric flow, sitting in Neptune's southern hemisphere with wind speeds around its edges, reaching some of the highest velocities measured anywhere in the solar system. It was, in every sense of the word, a monster. Scientists naturally assumed it would persist. Jupiter's Great Red Spot, also an anticyclonic vortex, also embedded in a banded atmospheric flow, has been observed continuously for at least 350 years. Large storm systems on giant planets, it seemed reasonable to assume, were inherently stable and long-lived. The Hubble Space Telescope turned to Neptune in 1994, just 5 years after Voyager's flyby. The Great Dark Spot was gone, completely and utterly gone, not shrunken, not diminished, absent. Not a trace of it remained in Neptune's atmosphere. The Earth-sized storm had simply vanished in less than a decade. This was shocking, and it remains, in some sense, unexplained. We don't have a complete model that explains why Neptune's storm systems are so transient compared to Jupiter's. The two planets have different atmospheric structures. Neptune lacks the rigid, stable east-west banding that characterizes Jupiter's atmosphere, and this difference is probably relevant. But the exact physical mechanism by which Neptune fails to sustain large vortices the way Jupiter does, despite having even more vigorous atmospheric circulation, is still being worked out. And then, to make things more interesting, new dark spots appeared. Hubble has observed multiple new dark spot events on Neptune since Voyager's flyby. A dark spot discovered in 2018 was tracked for years by ground-based and space-based observatories, giving scientists the first opportunity to watch the life cycle of one of these features in something approaching real time. And the behaviour was surprising, not because the storm dissipated, which everyone expected, but because of how it dissipated. As the dark spot drifted toward Neptune's equator, where models predicted it should break apart, it instead appeared to generate a companion bright cloud feature, a secondary structure that interacted with the main vortex in ways that existing models had not predicted. Neptune keeps rewriting the models. Every detailed observation we make of its atmospheric dynamics reveals something that our existing theories didn't anticipate. There was also a charming discovery by Voyager 2, a small, bright cloud feature in Neptune's southern hemisphere that mission scientists immediately christened the Scooter because of its extraordinary speed. The Scooter was visibly lapping other atmospheric features as Voyager watched, zooming around the planet at a rate far exceeding the already supersonic background winds. It was thought to be a convective cloud, a column of warm gas rising rapidly from deeper in the atmosphere, pushing a bright cloud ahead of it like a chimney pushing smoke, being swept around the planet by the ambient wind field. A beautiful, visible demonstration of Neptune's internal heat, pushing its way up through the atmosphere and interacting with the dynamics at the cloud level. Neptune also has seasons, and the implications of those seasons are almost philosophically overwhelming when you sit with them long enough. Because Neptune's rotation axis is tilted by approximately 28.3 degrees, remarkably similar to Earth's axial tilt of 23.5 degrees, Neptune experiences seasons in essentially the same geometric way Earth does. When the northern hemisphere is tilted toward the Sun, it receives more solar energy and experiences summer. When it's tilted away, it's winter. The mechanism is completely familiar. What is not familiar is the timescale. A Neptune year, one complete orbit of the Sun, takes 164.8 Earth years. Neptune completed its first full orbit since its discovery in 2011. Depending on your age, Neptune may have travelled only a fraction of the way around the Sun in your entire lifetime. And because the year is 164.8 Earth years long, each season on Neptune lasts approximately 40 years. A Neptunian winter, from first frost to last, spans 4 decades. A single summer on Neptune outlasts most human careers. The implications of 40-year seasons for atmospheric dynamics are profound and very poorly constrained. Seasonal variations in solar heating, even tiny ones because Neptune is so far from the Sun, accumulate over decades and can produce systematic changes in atmospheric temperature structure, in haze formation, in cloud distribution. These seasonal effects may be related to the appearance and disappearance of storm systems. They may drive long-period oscillations in wind speed. They may affect the chemistry of the upper atmosphere in ways that change Neptune's colour over time. But here is the fundamental problem. We have not been watching Neptune for long enough with good enough instruments to see a full seasonal cycle, modern detailed. Observations of Neptune have been possible for only a few decades. We are trying to understand a 40-year seasonal cycle with maybe 30 to 35 years of reasonably good data. It is like trying to understand Earth's full annual cycle of seasons with only 10 months of weather data. You'd know that things are changing, but you'd be missing crucial parts of the picture. This is one of the core arguments that planetary scientists make for a dedicated Neptune mission. Not just a flyby, an orbiter, something that stays at Neptune long enough to actually observe the planet through a significant portion of its seasonal cycle, to watch storms form and dissipate, to track the long-term evolution of the atmosphere, to build the kind of continuous observational record that has been so transformative for our understanding of Earth's climate. We have that for Earth. We have decades of satellite data, continuous atmospheric measurements, long-term monitoring of every layer of the atmosphere. We have built detailed climate models verified by observation. We have nothing remotely approaching that for Neptune, and Neptune, as the most extreme example of an ice giant planet, a planet type that appears to be one of the most common in the galaxy, deserves that kind of sustained attention. It just hasn't gotten it yet. Chapter 4. Neptune's magnetic field is broken, and nobody knows how to fix it all right. We've talked about Neptune's violent weather. We've talked about its exotic interior. Now I want to talk about something that doesn't get nearly enough attention in popular science coverage of Neptune. Something that planetary scientists find genuinely deeply troubling in the most exciting way possible. Neptune's magnetic field makes no sense. Let me explain what I mean by that, and why it matters so much. Every planet with a significant magnetic field generates that field through essentially the same mechanism. Deep inside the planet, there is a region of electrically conducting fluid. On Earth, that conducting fluid is the liquid iron nickel outer core. On Jupiter and Saturn, it's metallic hydrogen, a state of hydrogen that forms under extreme pressure where the electrons become delocalized and the material conducts electricity like a metal. The key ingredient is the conducting fluid, and when that conducting fluid moves, driven by heat rising from the even deeper interior, or by the planet's rotation, or by both, the motion of the electrical charges within it generates a magnetic field. This process is called the dynamo mechanism, and it is the standard, well-established explanation for why planets have magnetic fields. Now, the dynamo mechanism has a natural consequence. Because the fluid is deep inside the planet near the center, and because the planet's rotation tends to organize the fluid motions in a particular way, preferentially aligned with the rotation axis, the magnetic field that gets generated should be roughly aligned with the planet's spin axis. It doesn't have to be perfectly aligned. Earth's magnetic North Pole is currently about 11 degrees away from the geographic North Pole, and it wanders around over time, but the rough alignment should be there because the physics that generates the field is fundamentally tied to the planet's rotation. Jupiter's magnetic field is tilted by about 10 degrees from its rotation axis. Saturn's is tilted by less than 1 degree, almost perfectly aligned. Even accounting for some variability, the pattern holds. Giant planets have magnetic fields that are approximately, more or less aligned with their spin axes. Neptune's magnetic field is tilted by 47 degrees from its rotation axis. Not 10 degrees, not 15 degrees, 47 degrees. That is more than halfway to being perpendicular to the rotation axis. Neptune's magnetic poles are not near its geographic poles. They are not even in the same hemisphere as the geographic poles in any simple sense. The magnetic field axis cuts across the planet at an extreme angle. Take a moment to really visualize what that means. Imagine Earth, with its geographic North Pole at the top and the South Pole at the bottom. Now imagine tilting the entire magnetic field, the dipole axis, the line connecting the North Magnetic Pole to the South Magnetic Pole, by 47 degrees, so that the North Magnetic Pole is somewhere over Canada and the South Magnetic Pole is somewhere under the Indian Ocean. The magnetic and geographic coordinate systems are completely misaligned. That is the situation on Neptune. But, and this is where it gets even stranger, the tilt is only the beginning of the strangeness. On Earth, the The source of the magnetic field is the liquid outer core, which is located at the center of the planet. The field emanates from the center. This means that to a good approximation, Neptune's magnetic field should look like a simple dipole. Two poles, north and south, with field lines running cleanly from one to the other, centered on the middle of the planet. Like a bar magnet placed at the planet's center, Neptune's magnetic field is not centered on the planet. The center of Neptune's magnetic dipole is offset from the center of the planet by approximately 0.55 Neptune radii, more than halfway from the center to the surface. The mathematical center of the magnetic field is not at the center of the planet. It is displaced enormously, sitting far off to one side of the actual geometric center. The combination of a 47-degree tilt and a 0.55 radius offset creates a magnetic field topology that is extraordinarily complex. As Neptune rotates, once every 16.11 hours, this tilted, off-center magnetic field sweeps around through space like a badly aimed lighthouse beam. Different regions of Neptune's surface experience wildly different magnetic field strengths at different times during the day. At some locations on Neptune's surface, the magnetic field points outward from the planet. At nearby locations, it points inward. The field strength varies by a factor of more than 10 from the strongest to the weakest regions. The magnetic equator, the line of zero field dip where the field is horizontal, is not a simple circle around the planet's waist. It is a complex, irregular curve that weaves around the planet. This is unlike anything we see at Jupiter, Saturn, or Earth. It is deeply anomalous. The one comparison that does work, and it is both comforting and deeply significant, is Uranus. Uranus has a magnetic field tilted by approximately 59 degrees from its rotation axis, offset from the center by about 0.3 Uranus radii. Like Neptune, Uranus has a dramatically tilted, significantly offset magnetic field that looks nothing like the fields of the gas giants. The fact that both ice giants share this unusual magnetic field architecture is almost certainly not a coincidence. It is telling us something fundamental and specific about ice giants as a class of object, something about their internal structure that is genuinely different from gas giants, something that produces a fundamentally different kind of dynamo. The leading theoretical framework is that Neptune's magnetic field is not being generated in a metallic core, the way Earth's field is generated in its liquid iron core. There is probably no region of metallic hydrogen in Neptune's interior, because Neptune is not massive enough to compress hydrogen to the pressures needed to make it metallic. That requires the extreme mass of Jupiter or Saturn. Instead, Neptune's dynamo is thought to be operating in the exotic icy mantle we discussed in the previous chapter, specifically the supersonic water layer, where oxygen atoms form a crystalline lattice and hydrogen protons flow freely, may be electrically conducting enough to sustain a dynamo. But this would be a very different kind of dynamo from the ones we are most familiar with. Instead of operating in a spherical shell deep at the center of the planet, it would be operating in a thick layer partway through the mantle, displaced from the center, at a boundary between different phases of the interior ices. This geometry, a dynamo operating in a thick shell rather than a sphere, not centered on the planet's center, could naturally produce a magnetic field that is both tilted and offset. Some theoretical models of this kind of mantle dynamo have had some success in reproducing certain features of Neptune's and Uranus's magnetic fields, but we do not yet have a complete, fully validated model that self-consistently explains all the properties of Neptune's magnetic field from first principles. The mantle dynamo hypothesis is compelling and probably on the right track, but the details are still being worked out. Why does any of this matter? Why should you care about the orientation of Neptune's magnetic field? It matters for several reasons that go well beyond Neptune itself. First, the magnetic field is one of our most powerful diagnostic tools for probing a planet's interior. We cannot see into Neptune's interior, we cannot send a probe down there, but the magnetic field that Neptune generates in its interior leaks out into space and can be measured remotely. The structure of that field, its strength, its orientation, its complexity, how it changes with time, encodes information about the conducting regions of the interior, their depth, their size, their electrical properties, their temperature. Understanding Neptune's magnetic field more precisely and more completely would give us a window into the exotic physics of the high-pressure ices in the mantle. It would let us test whether the supersonic water hypothesis is correct. It would let us map the internal heat distribution of the planet in ways no other measurement can. Second, as we've mentioned, ice giants are probably the most common type of planet in the galaxy. The exoplanet surveys have found that planets in the Neptune to Uranus size range, often called sub-Neptunes or mini-Neptunes, are extraordinarily common around other stars. Many of the closest exoplanets to Earth are in this size range. If we want to understand the internal structure and evolution of the most common class of planets in the universe, we need to understand the magnetic fields of ice giants. And we can only study magnetic fields in detail for planets close enough to visit with spacecraft. Neptune is the best, and currently only realistic, ice giant laboratory we have. Third, Neptune's complex and rapidly varying magnetic field creates an extraordinarily dynamic magnetosphere, the region of space dominated by the planet's magnetic field, where solar wind particles are deflected and trapped. As Neptune's tilted, offset magnetic field sweeps around during the planet's 16-hour rotation period, it interacts with the solar wind and with Neptune's moons in complex, time-varying ways. The radiation environment near Neptune changes dramatically over the course of a single Neptunian day. This has direct implications for understanding how radiation belts form around ice giants, how energetic particles are accelerated and transported in these unusual magnetic geometries, and how the magnetospheres of ice giant exoplanets might look from the outside. Information that could eventually be useful in characterizing the space environments of exoplanets and their potential habitability. Neptune's weird magnetic field is not a curiosity. It is a laboratory for new physics, and it is a laboratory we have barely begun to use. Chapter 5: The Rings. Nobody talks about. Here is a question I want you to answer quickly without thinking about it too hard. Which planets have rings? You said Saturn. You almost certainly said Saturn first, and you may have stopped there. If you're a space enthusiast, maybe you added Jupiter and Uranus, but I would be willing to bet that most people watching this video did not immediately say Neptune. And yet Neptune has rings, a complete, complex, scientifically fascinating ring system that most people have never heard of. Neptune's rings are not like Saturn's rings. Saturn's rings are brilliant, highly reflective, made of water ice particles that efficiently scatter sunlight back toward us. They are so bright and so geometrically perfect that even a small amateur telescope can reveal them in stunning detail. Saturn's rings are one of the most visually impressive objects in the solar system, and they have been observed and studied for centuries. Neptune's rings are essentially the opposite of all that. They are dark, made of particles with very low reflectivity, probably organic compounds or silicates that absorb most of the light that hits them, rather than reflecting it. They are narrow, not the broad sweeping disk of Saturn, but a series of thin, distinct bands. They are faint, capturing only a tiny fraction of the sunlight that reaches them and sending even less back toward us. They are invisible to the naked eye, essentially invisible even through large ground-based telescopes under normal circumstances, and they were only definitively confirmed to exist when Voyager 2 flew through the Neptune system in 1989. Although, and this is an interesting historical footnote, there had been suggestive evidence for them before Voyager. In the 1980s, astronomers were using a technique called stellar occultation to study Neptune's atmosphere, watching carefully as Neptune passed in front of a distant star, observing exactly how the star's light faded and recovered as Neptune's atmosphere crossed in front of it. During some of these observations, the star's light would briefly dip and recover before Neptune's disk reached it, suggesting that something was blocking the starlight at a distance from Neptune itself, something in orbit around the planet. The results were puzzling and inconsistent, with the dips appearing on some sides of Neptune during some occultations but not others. This was deeply confusing, because a complete ring should block starlight symmetrically on both sides of the planet. As it turned out, the reason the occultation results were inconsistent was something genuinely remarkable, and it brings us to the most scientifically interesting feature of Neptune's ring system. Neptune has 5 main-named rings. Starting from closest to the planet and moving outward, they are the Gaia ring, the Leverrier ring, the Lassell ring, the Arago ring, and the Adams ring. They are named for people connected to Neptune's discovery. Leverrier and Adams, naturally, but also Gaia, the astronomer who actually found the planet, and Lassell, who discovered Triton. The naming convention is a diplomatic minefield given the contested history of the discovery, but it has stuck. The innermost ring, Gala, is a broad diffuse ring of very faint material, barely detectable even in Voyager's images. Leverrier is narrow and denser. Lassell is a broad plateau of diffuse material between Leverrier and Arago. Arago is another narrow ring. And then there is Adams, the outermost of the main rings, and by far the most scientifically interesting. The Adams ring is the reason the stellar occultation results before Voyager were so confusing. Because the Adams ring is not uniform. Around most of its circumference, the Adams ring is a narrow but relatively normal ring. Particles distributed around the orbit in a roughly even way. But in certain specific regions, the particle density is dramatically higher. The ring has concentrated clumps of material, arcs of much denser structure embedded within the broader ring. And because these arcs are concentrated in specific locations, when Neptune passed in front of a star and an arc happened to be on the side between Earth and the star, you'd see a dip in the starlight. When no arc was present on that side, you wouldn't. The seemingly random, inconsistent occultation results were actually the signatures of discrete arc structures within the ring. These arcs have been given names: Liberty, Equality, Fraternity, and Courage, named in recognition of their discovery by a French observational team, the names evoking the ideals of the French Revolution. The Liberté, Égalité, Fraternité of French national identity, plus a fourth arc for good measure. The arcs are scientifically extraordinary. Here is the problem they pose. In any ring system, particles are always moving. They have slightly different orbital speeds, slightly different orbital paths, slightly different responses to perturbations from moons and from each other. Over time, these small differences cause particles to spread out along their orbits. A concentrated clump of ring particles should diffuse outward along the ring, gradually smearing into a more uniform distribution. This process, called azimuthal spreading, should happen on timescales of years to decades. Clumps shouldn't persist, and yet the Adams ring arcs have been observed now for decades. They were seen by Voyager in 1989. They were observed by ground-based telescopes in subsequent years. They were imaged by the Hubble Space Telescope. In 2022 and 2023, the James Webb Space Telescope, with its extraordinary sensitivity in the infrared, captured stunning images of Neptune's ring system that showed the Adams ring arcs with unprecedented clarity. The arcs are still there. They have persisted far longer than simple orbital mechanics says they should. The leading explanation for the arc's persistence involves the moon Galatea. Galatea is a small inner moon of Neptune that orbits just slightly inside the Adams ring. Its orbital period is in a specific numerical ratio with the orbital period of ring particles in the Adams ring, a ratio close to 42 to 43, meaning that Galatea completes 42 orbits in nearly the same time it takes Adams ring particles to complete 43 orbits. This is an orbital resonance, and orbital resonances create gravitational patterns. In this case, the resonance creates a series of gravitational corrals, regions of space where the gravitational perturbation from Galatea creates stable pockets, locations where particles are gravitationally herded and held rather than being allowed to spread freely. The arcs are thought to sit within these gravitational corrals, maintained against the tendency to spread by Galatea's continuous gentle shepherding. The mathematics of this resonance mechanism are beautiful in their complexity, a delicate gravitational clockwork that has been ticking for potentially millions of years. But the mechanism has not been fully validated. Detailed dynamical models of the Galatea-Adams ring interaction have had some success in explaining the existence of the arcs, but have struggled to explain all their properties, their exact extent, the spacing between them, how they have evolved over time. Some recent observations suggest the arcs may be slowly changing, potentially losing material or shifting in position, which would tell us something about how the Shepherd Moon mechanism operates over long timescales. The James Webb Space Telescope observations of Neptune's rings in 2022 were genuinely revelatory in a way that deserves more attention than it got. JWST observes primarily an infrared light, and Neptune's rings, being dark at optical wavelengths, are relatively brighter at infrared wavelengths. The JWST images showed the rings with a clarity and detail that surpassed Voyager's observations in some respects, and they revealed structural features and variations in the ring system that will keep researchers busy for years. JWST continues to be used to monitor Neptune's rings, building a baseline of observations that will eventually allow scientists to track how the ring system evolves over time, something that has never been possible before. Neptune's rings are a reminder that even in our own solar system, in a place we have largely neglected, there are structures of extraordinary complexity and beauty that we are only beginning to understand. The Adam's ring arcs are one of the great unsolved problems of solar system dynamics, and they are sitting there, going around Neptune once every 7 hours or so, waiting for us to pay more attention. Chapter 6: Triton, the moon that shouldn't exist. Now we get to Triton, and I have been looking forward to talking about Triton since the beginning of this video, because Triton is, without any exaggeration, without any hyperbole, with complete scientific sincerity, one of the most extraordinary objects in the solar system. Triton is strange in ways that are immediately obvious, strange in ways that take a moment to appreciate, and strange in ways that have profound implications for astrobiology and the search for life beyond Earth. Let's start with the most immediately obvious strangeness. Triton orbits Neptune backwards. Every major moon in the solar system orbits its parent planet in the same direction that the parent planet rotates. This is not a coincidence. It is a consequence of how moons form. Moons generally form from the same disk of material that surrounded a young planet in the early solar system, and that disk rotates in the same direction as the planet. So the moons that form from it inherit that rotational direction. This is called prograde orbit, and it is the rule for large moons throughout the solar system. Earth's moon, Jupiter's 4 Galilean moons, Saturn's Titan, all prograde, all orbiting in the same direction as their planet's rotation, all consistent with having formed from a primordial circumplanetary disk. Triton orbits Neptune in the opposite direction. It is in a retrograde orbit, going around Neptune the wrong way against Neptune's spin, and Triton is big, very big. Triton has a diameter of about 2,700 kilometers, making it the 7th largest moon in the solar system, bigger than Pluto, bigger than Eris, comparable in size to several of the large moons of Jupiter and Saturn. It is not a small, irregular captured object. It is a major moon, a world-sized body, orbiting backwards. A large moon on a retrograde orbit cannot have formed from a circumplanetary disk. It is impossible. The disk rotates prograde, and everything that forms from it inherits that direction. A retrograde moon had to come from somewhere else. It had to be captured, pulled in from an independent orbit in the outer solar system, grabbed by Neptune's gravity at some point in the distant past. This is the capture hypothesis for Triton, and it is the consensus view among planetary scientists. Triton was not born in orbit around Neptune. It was born elsewhere in the outer solar system, most likely in the trans-Neptunian region, the same cold, dark population of icy bodies that Pluto belongs to. Triton, based on its composition and properties, was probably once a Pluto-like object, a large Kuiper belt body, orbiting the Sun independently in the outer reaches of the solar system, and at some point, probably in the first few 100 million years of the solar system's history, when things were generally more chaotic and dynamically eventful, Triton had an encounter with Neptune that resulted in its capture into orbit. The exact mechanism of capture is a subject of ongoing research and debate, because capturing a large body from a hyperbolic trajectory into a bound orbit is gravitationally non-trivial. You can't just have Neptune and Triton interact gravitationally, because a two-body gravitational interaction is mathematically reversible. If Neptune doesn't have enough mass to pull Triton in, and Triton doesn't slow down, it will just fly past and continue on its way. To capture Triton, something has to carry away the excess energy and momentum of Triton's original solar orbit. Options include a collision or close encounter between Triton and another large body already in the Neptune system, a three-body gravitational interaction involving Neptune, Triton and another object, or possibly capture during a period when Neptune had an extended dissipative disk of material. The leading hypothesis currently involves Triton having been part of a binary system, two large Kuiper belt objects gravitationally bound to each other, that encountered Neptune. The gravitational interaction broke up the binary, with one body being flung away and the other, Triton, being captured. This binary capture mechanism is mathematically plausible, and is consistent with the orbital dynamics observed. But whatever the specific mechanism, Triton's capture had profound consequences for the Neptune system. A large body arriving on a retrograde orbit would have swept through the region of space where prograde moons might have been forming or already existed, disrupting or destroying any original satellite system Neptune might have had. This is why Neptune's inner moon system, the small moons that orbit close to the planet, is thought to be composed of fragments of objects that were shattered and recombined after Triton's arrival, rather than original moons that formed with Neptune. The Neptune system we see today is largely a reconstruction, a rebuilt satellite system that emerged from the debris of the chaos Triton's capture created. Triton's post-capture orbit was also highly eccentric and inclined at first. The same gravitational interactions that captured it left it on an elongated, inclined path that cut through the inner Neptune system. But tidal interactions, the gravitational flexing and squeezing of Triton by Neptune's gravity as it moved through its eccentric orbit, gradually dissipated energy and circularized the orbit over hundreds of millions of years. Today, Triton's orbit is almost perfectly circular, at an inclination of about 157 degrees to Neptune's equatorial plane, almost perfectly circular, tidally evolved, calm. But the history written in that orbital geometry is extraordinary. Now, here is where Triton's story takes a turn from fascinating origin story to potentially profound implications for the search for life. That tidal heating during the period when Triton's orbit was being circularized was not trivial. The same process that circularized Io's orbit around Jupiter heats Io so intensely that it is the most volcanically active body in the solar system, more volcanically active than Earth, covered in erupting volcanoes and flooded by lakes of silicate lava. Triton experienced a similar process, and even today, with its orbit nearly circular, Triton continues to be heated by tidal interactions with Neptune, though at a much reduced level compared to the early phase of orbital circularization. The question that this raises, and that planetary scientists take very seriously, is whether Triton might have, or might once have had, a liquid water ocean beneath its icy surface. Europa, one of Jupiter's moons, has a confirmed subsurface liquid water ocean maintained by tidal heating from Jupiter. Enceladus, a moon of Saturn, has a subsurface ocean and is actively venting water into space through geysers. The existence of subsurface liquid water oceans maintained by tidal heating appears to be a recurring feature of the outer solar system, and Triton, with its history of intense tidal heating, has good reason to be on that list. And here is the thing that pushes this from speculation into something more concrete. Voyager 2 actually observed active eruptions on Triton's surface. When Voyager flew past in 1989, it imaged Triton's surface in detail, and it found something remarkable. Dark plumes rising from the surface, geysers erupting from specific locations near the South Pole and sending dark, streaky material kilometers into the sky before being caught by the thin Tritonian wind and swept downwind. Active geological processes on a world in the outer solar system at a temperature of about 38 Kelvin, one of the coldest surfaces in the solar system. These geysers are thought to be nitrogen geysers, driven by the sublimation of nitrogen ice near the surface, when sunlight, even the faint sunlight at Neptune's distance, warms dark patches on the surface through a kind of greenhouse effect beneath the translucent nitrogen ice. Solar-powered nitrogen geysers at 38 Kelvin are already remarkable, but the existence of any geological activity at all on Triton's surface, any active process moving material around, suggests that Triton is not the inert, frozen, dead world you might expect from a moon at the edge of the solar system. Triton's surface is also very young in geological terms. Voyager images showed remarkably few impact craters, far fewer than you'd expect on a surface that had been passively accumulating impacts for billions of years. This implies that geological processes have been resurfacing Triton relatively recently, erasing old craters and replacing them with fresh surface material. The cantaloupe terrain, as geologists call it, a strange dimpled surface texture that covers large areas of Triton and looks strikingly like the skin of a cantaloupe melon, is thought to be the result of a process called diaporism, where warmer material from below rises through the crust and deforms the surface. This is internal geological activity. This is Triton's interior interacting with its surface. And if Triton's interior is geologically active, if there is heat inside and processes moving material around, The question of whether there might be a liquid water layer somewhere beneath the surface becomes much less far-fetched. There is another dimension to Triton's astrobiology potential that rarely gets mentioned. Triton is on a decaying orbit. Because its orbit is retrograde, going the opposite direction from Neptune's rotation, the tidal forces between Triton and Neptune act as a brake on Triton's orbital motion, rather than an accelerant. For prograde moons, tidal interactions can gradually push them outward over time, as the moon is slowly receding from Earth. For Triton, with its retrograde orbit, the tidal interaction is slowly pulling it inward. Triton is spiralling toward Neptune on a geological timescale. In approximately 3.6 billion years, well within the future lifetime of the solar system, Triton will cross the Roche limit, the distance from Neptune within which Neptune's tidal forces are stronger than the self-gravity holding Triton together. At that point, Triton will be torn apart. Neptune will gain a spectacular ring system, far more impressive than Saturn's current rings, as the material of Triton is spread around the planet in a brilliant disk. Triton is on death row. It has been since the moment it was captured, and the countdown has been running for billions of years. This doomed trajectory makes Triton one of the most bittersweet objects in the solar system. Here is a world, a complex geologically active world with a possibly habitable interior, with geysers erupting from its surface, with a fascinating history as a captured Kuiper Belt object, and it is going to be destroyed. Not imminently, not in any time frame relevant to human civilization, but certainly. Neptune is going to consume it. The scientific case for a Triton-focused mission is therefore not just about planetary science curiosity. It is potentially about astrobiology at the most fundamental level. If Triton has a subsurface liquid water ocean, and if that ocean has been maintained by tidal heating throughout Triton's billions of years in the Neptune system, then it is an environment where the basic conditions for life as we understand them, liquid water, energy from geological activity, chemical complexity, may be present. A dedicated Triton lander or subsurface probe would be one of the most consequential astrobiology missions conceivable. We have exactly 0 such missions planned. Chapter 7. Where did Neptune come from? The migration that changed everything. Up to this point, we've been talking about what Neptune is and what it does. Now I want to talk about something equally profound, how Neptune got to where it is. Because Neptune did not form where it currently lives, and the story of how it got here is the story of how our entire solar system became the place it is today. This is the story of the Nice model, named not for a particularly enthusiastic opinion of it, but for Nice, the city in southern France where the theorists who developed it were based. And it is a story of cosmic violence on a scale that is almost impossible to fully appreciate. The early solar system, in the first few 100 million years after the Sun formed, looked very different from the solar system we live in today. The 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, were not where they are now. According to the Nice model and its successors, the giant planets were all much closer to the Sun, packed into a much more compact configuration in the region that is now the outer solar system. Neptune, in particular, is thought to have formed at somewhere between 15 and 20 astronomical units from the Sun, roughly where Uranus is today, not at 30 astronomical units where it lives now. Beyond the giant planets, in the early solar system, was an enormous disk of icy planetesimals, trillions of small icy bodies left over from the formation of the planets. This is the primordial Kuiper Belt, or the primordial trans-Neptunian disk, and it contained perhaps 20 to 50 Earth masses of material spread over a vast region of space. For hundreds of millions of years, this arrangement was roughly stable. The giant planets orbited the Sun in their compact configuration. The icy disk sat beyond them. There was some slow gravitational interaction between the planets and the disk, with the disk gradually feeding icy planetesimals into the inner solar system, and the giant planets gradually adjusting their orbits in response. But the changes were slow, and the system maintained some semblance of order. And then Jupiter and Saturn crossed a resonance. As Jupiter and Saturn slowly drifted in their orbits due to interactions with the planetesimal disk, their orbital periods gradually approached a simple numerical ratio, specifically approximately 2:1, meaning Jupiter completed almost exactly 2 orbits for every one Saturn orbit. This is called the 2:1 mean motion resonance, and crossing through it is like hitting a trigger. The The gravitational interaction between Jupiter and Saturn at this resonance became very strong, and it dramatically destabilized both planets' orbits, exciting them to higher eccentricities and changing their semi-major axes significantly. The effect of Jupiter and Saturn's orbital destabilization rippled outward through the solar system like a shockwave. Uranus and Neptune, which had been quietly orbiting beyond Saturn, suddenly found themselves in a gravitationally chaotic environment. They began interacting strongly with each other and with the icy planetesimal disk. They scattered planetesimals inward toward the inner solar system and in reaction were themselves pushed outward. This outward migration of Uranus and Neptune was not slow and gentle. The Nice model describes it as rapid and dramatic. In a geologically short period of time, perhaps a few million to a few tens of millions of years, the ice giants migrated outward substantially, ploughing through and scattering the primordial icy disk. Neptune, the outermost giant, migrated the most dramatically, pushing outward from its formation region around 15 to 20 astronomical units to its current position at about 30 astronomical units. As Neptune migrated outward through the icy disk, it didn't just push through it passively. It captured some of the icy bodies into resonant orbits, gravitational configurations where the orbital period of the icy body is in a simple ratio with Neptune's orbital period, and where the gravitational interaction tends to maintain and protect that relationship rather than disturbing it. Pluto's the most famous example of a resonance capture by Neptune. Pluto is in a 2 to 3 resonance with Neptune, meaning it completes exactly 2 orbits for every 3 of Neptune's. This resonance has kept Pluto in a stable, protected orbit for billions of years, preventing Neptune from scattering it out of the solar system entirely. The outward migration of Neptune also sent a torrent of icy bodies flying inward toward the inner solar system. This may be the explanation for an event called the Late Heavy Bombardment, a period about 3.9 billion years ago when the Moon and the inner planets were subjected to an intense barrage of impacts, leaving the Moon's surface cratered in the way we see it today. The geological record on Earth and the other inner planets shows evidence of this bombardment period. If the Nice model is correct, Neptune's migration was partly responsible for triggering this bombardment by scattering the primordial icy disk inward. This means Neptune's migration may have profoundly affected the early Earth. The bombardment it helped trigger may have delivered water to the early Earth, water that became our oceans. It may have delivered organic compounds that were relevant to the emergence of life, or it may have sterilized the early Earth repeatedly, resetting the conditions for life again and again. The relationship between Neptune's migration and the early history of life on Earth is something that planetary scientists and astrobiologists are actively investigating, and it is one of the most profound questions that studying Neptune can help us answer. Neptune's current position at 30 astronomical units was not inevitable. It was the result of a specific sequence of dynamical events in the early solar system, a chaotic contingent process that could have turned out differently. If Neptune had migrated differently, the entire solar system architecture would be different. The Kuiper belt would be different, the late heavy bombardment would have been different, the delivery of water and organics to the inner solar system would have been different, the early conditions on Earth would have been different. Neptune, sitting quietly at the edge of the solar system, is in some sense the fingerprint of the dynamical history of everything. Understanding how it got where it is helps us understand how our solar system, and by extension, how solar systems in general, evolved from their early chaotic states into the more ordered configurations we observe billions of years later, and understanding how our solar system specifically evolved is directly relevant to understanding how Earth became habitable and why. The grand arc from Neptune's mathematical discovery in 1846 to its role as a key witness to the early history of the solar system is one of the most remarkable stories in all of science. A planet found by mathematics alone, orbiting at the frozen edge of the solar system, revealed to be the driver of a cosmic reorganization that helped shape the conditions for life on Earth. Not boring, not quiet, extraordinary. Chapter 8. The one time we actually went there. Voyager 2's 6 hours that changed everything. August 25th, 1989. A spacecraft called Voyager 2 is travelling through the outer solar system at approximately 60,000 kilometers per hour. It has been in space for 12 years. It launched in 1977, flew past Jupiter in 1979, past Saturn in 1981, past Uranus in 1986. It has been travelling for over a decade, crossing distances that no human-made object had ever crossed before, running on a nuclear power source that generates electricity from the heat of decaying plutonium, controlled by onboard computers whose processing power is laughably inferior to the phone in your pocket, communicating with Earth across billions of kilometres of empty space using a radio transmitter about as powerful as a refrigerator light bulb. And on August 25, 1989, Voyager 2 makes its closest approach to Neptune, passing within about 4,950 kilometres of the cloud tops. For a brief window of hours, humanity has a spacecraft in the Neptune system. For the first, and, as of this recording, the only time in history, we are actually there. What Voyager 2 accomplished during that encounter is nothing short of extraordinary. The sheer volume and quality of scientific discovery packed into those few hours of close observation is a testament to the ingenuity and dedication of the engineers and scientists who planned and executed the mission over the course of more than a decade. Before Voyager, Neptune was essentially a point of light, a blue dot in the telescope, barely resolved as a disk even by the most powerful ground-based instruments of the time. We knew it was blue, we knew its size approximately. We knew it had one confirmed moon, Triton, and possibly one other, Nereid. We knew its mass from its gravitational effect on Uranus. Beyond that, Neptune was a mystery, a planet about which almost nothing was directly known. After Voyager 2's flyby, we had a world. In the days and hours of the closest approach, Voyager's cameras resolved Neptune's atmosphere in detail for the first time. The great dark spot snapped into focus, an Earth-sized storm system with swirling cloud structures around its edges, moving at supersonic speeds. The scooter became visible, racing around the planet, a bright cloud feature unlike anything observed on any other world. Multiple layers of cloud structure emerged from the data, high, thin, cirrus-like clouds of methane ice, casting shadows on lower cloud decks, revealing the three-dimensional structure of the atmosphere in a way no Earth-based observation could have managed. Voyager's instruments measured the wind speeds for the first time directly, confirming the supersonic velocities that we've discussed at length in this video. The spacecraft's radio signals passing through Neptune's atmosphere during a technique called radio occultation allowed scientists to probe the atmospheric temperature and pressure structure with unprecedented precision. Neptune's atmospheric profile was revealed, how temperature changed with altitude, where the tropopause sat, how the stratosphere was structured. For a planet we had barely resolved as a disk 2 years earlier, this was an extraordinary leap in knowledge, the magnetic field. Voyager carried a magnetometer, and as the spacecraft entered Neptune's magnetosphere and swept through the system, it measured the structure and strength of the magnetic field in exquisite detail. The 47-degree tilt and the 0.55 radius offset that we discussed in Chapter 4, Voyager discovered those. Before Voyager, we knew Neptune had a magnetic field from radio emissions detected by ground-based radio telescopes. After Voyager, we had the detailed three-dimensional structure of that field mapped for the first time. The measurement of Neptune's magnetic field by Voyager 2 remains, to this day, the only direct in situ measurement of a magnetic field at Neptune. Everything else we know about it has been inferred from Earth-based radio observations. The rings. Voyager confirmed their existence definitively and revealed their structure, the 5 distinct rings, their widths, their relative brightness, their optical depth. Most importantly, Voyager revealed the Adam's ring arcs for the first time in direct imaging. Liberty, equality, fraternity, and courage. The concentrated clumps of material that had been hinted at by ground-based stellar occultation observations but never directly seen. The discovery of the arcs transformed our understanding of ring dynamics and posed the puzzle, which we discussed in Chapter 5, that researchers are still working to fully resolve: the moons. Before Voyager, we knew of 2 Neptunian moons, Triton and Nereid. Voyager discovered 6 more, all small inner moons orbiting within or near the ring system. Galatea, the proposed shepherd for the Adam's ring arcs, was among these discoveries. Proteus, the largest of the newly discovered inner moons, turned out to be bigger than Nereid. These inner moons, with their irregular shapes, dark surfaces, and complex orbital relationships with the rings, revealed a sophisticated inner satellite system that had been completely unknown before the flyby. and then there was Triton itself. Voyager's closest approach to Neptune was timed and targeted specifically to enable a close flyby of Triton, because mission planners understood that Triton, with its retrograde orbit, its hints of geological activity from Earth-based spectroscopy, its status as the largest moon in the system, was probably the most scientifically valuable target in the Neptune system. The trade-off was that approaching close to Neptune on a trajectory that then bent inward to pass near Triton was not the most efficient way to study Neptune itself, but the mission planners made the right call. Voyager passed Triton at a distance of about 40,000 kilometers, close enough to resolve the surface in detail, close enough for the cameras to pick out features as small as a few kilometers. What they saw remains one of the most striking and scientifically significant sets of images ever returned from the outer solar system. Triton's surface is extraordinarily complex. The cantaloupe terrain, that distinctive dimpled surface texture covering the Western Hemisphere, was unlike anything seen on any other body in the solar system. The Southern Hemisphere was covered by a pink-tinged polar ice cap of nitrogen and methane ice, relatively bright and smooth. And from specific locations near the boundary of this polar cap, dark material was being vented upward in the nitrogen geysers we discussed earlier, dark streaks extending downwind for hundreds of kilometers across the surface, evidence of active ongoing geological processes at a temperature of 38 Kelvin. Very few impact craters, a surface that has been geologically reshaped, a complex interior with a history of tidal heating, the potential for a subsurface ocean. Voyager handed planetary scientists a world of extraordinary complexity and handed astrobiologists a target of serious potential relevance, and then flew onward into interstellar space. The encounter lasted, in terms of the closest high-resolution observation phase, approximately 6 hours. 6 hours to reveal a planet and its system from near total obscurity into something approaching scientific understanding. 6 hours that produced enough data to keep researchers busy for decades. 6 hours that are still, 35 years later, the sum total of humanity's direct experience of the Neptune system. After the flyby, Voyager 2 continued outward. It crossed the heliopause, the boundary where the Sun's influence gives way to interstellar space, sometime around 2018. It is now in interstellar space, travelling at approximately 15 kilometers per second, and it is still operational, still sending back data. But it is not going back to Neptune. It will never go back to Neptune. What Voyager 2 showed us in 1989 was not a complete picture of Neptune. It was a tantalizing, extraordinary, revolutionary first glimpse, a snapshot, a portrait taken through a fast-moving window. Every discovery it made raised new questions, and almost none of those questions have been answered in the 35 years since. The great dark spot it photographed disappeared within 5 years. The magnetic field structure it measured has never been re-examined in situ. The rings it discovered have been monitored only from a distance, with instruments never designed for that purpose. Triton's geysers have never been imaged again at close range. We took one good look at Neptune, and then we left and never came back. And the reasons for that are worth examining honestly, because they say something uncomfortable about how we prioritize scientific exploration. Chapter 9. Why haven't we gone back? The politics and physics of deep space. Exploration. Here is a question that deserves a direct, honest answer. Why, in 35 years since Voyager 2's flyby, has no other spacecraft visited Neptune? The answer has several components, and some of them are more forgivable than others. The first component is physics. Neptune is very far away. At 30 astronomical units from the Sun, it takes a very long time to get there. Voyager 2, which used gravitational slingshot maneuvers around Jupiter, Saturn and Uranus to accelerate to the speeds needed to reach Neptune in a reasonable time, still took 12 years to make the journey. A conventional spacecraft launched on a direct trajectory to Neptune would take even longer, roughly 12 to 15 years at minimum, depending on launch window and propulsion capabilities. Space missions take a long time to plan and build as well. From concept to launch, a major planetary science mission typically takes 10 to 15 years. Add that to the travel time, and you're looking at 25 to 30 years from the moment someone starts seriously working on a Neptune mission to the moment data starts coming back. That is longer than most scientific careers, It requires an institutional commitment that transcends individual researchers, funding cycles, and political administrations. It requires the kind of sustained, multi-generational scientific planning that is genuinely difficult for human institutions to execute. The second component is money. Large planetary science missions, flagship-class missions like the Cassini mission to Saturn or the Galileo mission to Jupiter, cost in the range of several $billion. A flagship Neptune orbiter mission, with the complexity and instrumentation needed to do the science properly, would likely cost something in the range of $3 to $4 billion or more. That's a lot of money by any measure, and it competes for funding with every other scientific priority. Earth observation satellites, Mars missions, telescope programs, astrophysics, heliophysics, and more. In the United States, NASA's planetary science budget has fluctuated considerably over the decades, and flagship missions can only be afforded at a rate of roughly one at a time. Currently, the flagship mission in development for the outer solar system is the Europa Clipper, which launched in October 2024 and is designed to study Jupiter's moon Europa and its subsurface ocean. Before that, the Cassini mission at Saturn and the Juno mission at Jupiter consumed flagship-level resources. Neptune has consistently been outcompeted for the flagship slot by other targets that seemed, at the time, more immediately tractable or more politically compelling. The third component is the scientific priority landscape, which is complicated. The Decadal Survey, a process by which the American planetary science community collectively ranks its priorities and recommends them to NASA every 10 years, is the mechanism by which missions get prioritized. The 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, published in 2022, is the most recent edition, and for the first time, this Decadal Survey explicitly ranked a Neptune system orbiter as the second highest priority flagship mission for the coming decade, behind only the Uranus orbiter and probe mission. This was a historic moment. For the first time, the Neptune system received explicit high-level community endorsement as a priority target, but ranking second is not ranking first. The Uranus orbiter and probe was ranked first, partly because Uranus has been even less visited than Neptune. Voyager 2 flew past Uranus in 1986, also for only a few hours, and partly because the scientific case for distinguishing the two ice giants by visiting both is compelling. Understanding why Uranus has no significant internal heat source, while Neptune has substantial internal heating, requires visiting both. The Uranus mission got the top slot, Neptune got second place. What this means practically is that even with the community prioritization in place, a Neptune orbiter mission is unlikely to launch before the late 2030s at the absolute earliest, and more likely sometime in the 2040s, which means, accounting for travel time, it would not arrive at Neptune until the 2050s or 2060s. People who are in graduate school right now studying Neptune may be retired before data from a dedicated Neptune orbiter starts flowing. This is not a comfortable situation, and the scientific community knows it. There are also technical challenges that deserve acknowledgement. At Neptune's distance from the Sun, solar power generation becomes completely impractical. The sunlight is simply too faint to generate meaningful power from solar panels at any reasonable panel size. Any spacecraft going to Neptune needs a nuclear power source, specifically a radioisotope thermoelectric generator that converts heat from decaying plutonium into electricity. These RTGs are not freely available in unlimited quantities. The United States has been producing new plutonium-238, the specific isotope needed for RTGs, at limited rates, and the supply is carefully managed and allocated. A Neptune mission would need a substantial plutonium allocation, competing with other deep space missions. The communication challenge is also real. At 30 astronomical units, radio signals travelling at the speed of light take about 4 hours to reach Neptune. That means a round-trip communication delay of 8 hours. Commands sent from Earth take 4 hours to arrive, and the responses take another 4 hours to come back. This makes real-time control of a spacecraft at Neptune impossible. Everything has to be programmed in advance, and the spacecraft has to be capable of operating autonomously for extended periods. This is manageable with modern technology, but it requires careful mission design and robust onboard autonomy systems. All of these challenges are real. None of them are insurmountable. Every single one of them could be overcome with sufficient resources, will, and time. The physics of getting to Neptune is understood. The engineering of spacecraft that can survive the journey and operate at that distance is understood. The science return from such a mission would be extraordinary. The only genuine bottleneck is the combination of funding constraints and competing priorities, and there is an argument, a serious scientific argument, not just an emotional one, that Neptune deserves to be higher on the priority list than it currently is. That argument goes like this. Neptune is the best representative of the ice giant class of planets in our solar system. Ice giants are the most common type of giant planet in the galaxy. Understanding ice giants, their interiors, their magnetic fields, their atmospheric dynamics, their moon systems, is not just about Neptune. It is about understanding the most common class of planets in the universe. Every Neptune question we answer has implications for thousands of exoplanets we have detected around other stars but cannot study in detail. The science returned from a Neptune orbiter would extend far beyond the Neptune system itself. It would be a lens through which we understand ice giants everywhere. That is not a small thing. That is one of the core scientific motivations for exploring the outer solar system at all. Chapter 10. What a real Neptune mission would look like. Let's talk about what actually going back to Neptune would mean. Not in vague terms, but concretely. What would a real dedicated Neptune mission look like? What would it do? What would it answer? The planetary science community has studied this question extensively, and there are several well-developed mission concepts that have been analysed in detail. The most comprehensive option is an orbiter, a spacecraft that travels to Neptune and enters orbit, remaining in the Neptune system for years rather than flying through in a matter of hours. An orbiter fundamentally transforms what you can learn about a planet compared to a flyby. With an orbiter, you can observe the same features repeatedly, tracking how they change over time. You can observe Neptune's atmosphere over months and years, watching storm systems form and dissipate, tracking seasonal changes, building a statistical understanding of the weather patterns. You can monitor the magnetic field continuously, watching how it varies with Neptune's rotation and how it responds to changes in the solar wind. You can orbit Triton multiple times, mapping its surface completely, measuring its shape precisely, studying its geyser activity in detail. A Neptune orbiter mission would likely carry a suite of instruments similar to what Cassini carried at Saturn. Cameras for visible and near-infrared imaging, a thermal infrared spectrometer to map atmospheric temperatures and composition, a magnetometer to measure the magnetic field continuously, a plasma science instrument to study the magnetosphere and charged particle environment, a radio science instrument that uses the spacecraft's radio signals to probe atmospheric structure and gravitational fields, an ultraviolet spectrometer to study the upper atmosphere, and possibly a near-infrared mapping spectrometer to study surface compositions of the moons. One of the highest priority instruments for a Neptune orbiter would be something capable of penetrating below Neptune's cloud tops, either a microwave radiometer that can sense thermal emission from deeper atmospheric layers, like the instrument on the Juno spacecraft at Jupiter, or a radio receiver that can detect lightning and radio emissions from deeper in the atmosphere. Neptune's visible cloud tops are only the thin outer layer of a vast atmospheric system. Getting information about what lies below, the temperature structure, the composition, the dynamics, is critically important for understanding Neptune as a whole. An orbiter might also release an atmospheric probe, a smaller spacecraft that separates from the main orbiter and plunges into Neptune's atmosphere, transmitting data as it descends before being crushed by the increasing pressure. Such a probe would be modelled on the Galileo atmospheric probe, which entered Jupiter's atmosphere in 1995 and transmitted data for about an hour before the pressure destroyed it. A Neptune atmospheric probe would directly measure the composition at depth, the abundances of helium, methane, and heavier elements, in ways that are impossible from remote sensing. These composition measurements would constrain models of Neptune's formation and evolution, telling us something about the primordial nebula from which Neptune formed and the conditions in the early solar system. For Triton, a flyby during the orbital tour at close range would be transformative, but the science community is also seriously discussing the possibility of a Triton lander, a spacecraft that could actually set down on Triton's surface and make direct measurements. This would be one of the most technically challenging and scientifically rewarding missions conceivable. A Triton lander sitting near the active geyser fields could directly sample the material being vented from the interior. It could measure the composition of Triton's ices, the temperature structure near the surface, the seismic activity of the Moon, the magnetic and plasma environment. If there is a subsurface ocean, if there is a liquid water environment beneath Triton's icy crust, a lander above it might be able to detect seismic signals from that ocean, or chemical signatures of ocean water being transported toward the surface. The technical challenges of landing on Triton are substantial. Triton's surface gravity is only about 8% of Earth's, which makes landing a manageable proposition in terms of propellant budget. But the surface is covered in nitrogen ice that may have an unpredictable structure, firm enough to support a lander or not. The temperature is 38 Kelvin, cold enough to make electronics behave in unexpected ways. The communication delay means the lander has to be completely autonomous during the landing sequence, and getting any significant mass to Triton's surface requires either a large, high-thrust propulsion system or very careful mission design. None of these challenges are unsolvable. All of them require engineering resources and time that are finite. A Triton lander is probably not a first mission. It is probably something that comes after an orbiter has mapped the surface in detail, identified the best landing sites, and characterized the surface properties well enough to design a landing system with confidence. But it is conceivable. It is within the reach of human technology, and the potential scientific payoff, the possibility of directly probing an environment that might be habitable, the possibility of sampling material from a captured Kuiper Belt object, the possibility of making in situ measurements of the most geologically complex world in the outer solar system, is extraordinary. There is also the question of what we might learn about Neptune's interior more directly. For Jupiter and Saturn, one technique that has been used to probe interior structure is precise measurement of the gravitational field, measuring tiny variations in the spacecraft's trajectory as it orbits close to the planet, which reflect the distribution of mass inside the planet. Juno has used this technique at Jupiter with spectacular success, revealing the deep structure of Jupiter's atmospheric dynamics and the fuzzy boundary of its core. A Neptune orbiter making close passes to the planet on highly elliptical orbits could similarly map Neptune's gravitational field in detail, constraining models of the internal density distribution and putting tighter limits on the size and composition of the core, the thickness of the various mantle layers, and the location of the dynamo region. Combined with the magnetic field measurements from a continuously operating magnetometer, the gravitational measurements from radio tracking, and the atmospheric composition measurements from a probe, a dedicated Neptune mission would transform our understanding of the planet's interior from the rough, uncertain sketch we currently have to something approaching a detailed portrait. This is what we're missing. This is the scientific opportunity that is sitting at 30 astronomical units, waiting. Every year that passes without a Neptune mission is a year of data we will never get back. A year of seasonal cycle we can't observe, a year of Triton's geyser activity we can't study. The planet is not getting more accessible with time, the science is not getting less important, but the missions keep getting deferred. Chapter 11. Neptune and the Search for Life in the Universe. Let me zoom out now, way out, past the Neptune system, past the solar system, out to the biggest question in planetary science, and arguably in all of science. Are we alone? The search for life beyond Earth, astrobiology, has been one of the organizing themes of planetary exploration for decades. Mars has been the dominant focus of this search for obvious reasons. It is close, it has evidence of ancient liquid water, it has a history of being more clement than it is today. The icy moons of Jupiter and Saturn, Europa, Enceladus, Ganymede, Titan, have become increasingly prominent as targets in the search for life because their subsurface oceans represent environments where liquid water, energy, and chemical complexity might coexist. Neptune, and specifically Triton, belongs in this conversation. Triton's potential subsurface ocean, maintained by tidal heating from Neptune, supplemented by radioactive decay in the rocky component of its interior, places it in the same category as Europa and Enceladus, a world where liquid water might exist beneath an icy crust, kept warm not by sunlight, but by internal geological processes. The same fundamental conditions that make Europa and Enceladus exciting astrobiology targets are potentially present at Triton. There is an additional dimension to Triton's astrobiological significance that is unique to its situation. Triton, as we discussed at length in Chapter 6, was almost certainly a captured Kuiper Belt object. It spent some unknown but probably substantial period of its history as an independent solar system body, orbiting the Sun in the same region as Pluto and the other trans-Neptunian objects. During that period, it was exposed to the same conditions as other Kuiper Belt objects, cosmic radiation breaking up surface molecules and building up complex organic compounds, the same chemical evolution that has been documented on other KBOs and on comets. When Triton was captured by Neptune and tidal heating began to intensify, it is possible, and this is speculative but serious speculation, that some of this accumulated surface organic chemistry was mobilized. Heat from the interior, rising through the icy mantle, could have brought liquid water into contact with the organic-rich surface layer. Liquid water plus organic compounds plus energy is, as far as we understand it, one of the basic recipes for prebiotic chemistry. The chemistry that precedes and enables the origin of life. We don't know if this happened on Triton. We don't have the data to evaluate it properly, but the theoretical possibility is real, and it is not absurd. It is the kind of possibility that, when it exists, scientists have an obligation to take seriously and to investigate. Neptune itself also appears in astrobiological discussions in a different way, as a template for understanding the internal structures and potential habitability of exoplanets. As we've mentioned throughout this video, subneptunes and mini-Neptunes are among the most common types of exoplanets detected around other stars. Some of these exoplanets orbit in the habitable zones of their stars, the regions where liquid water could in principle exist on a planetary surface or in a subsurface ocean. Understanding the interior structures, the magnetic environments, and the atmospheric compositions of ice giant planets at Neptune is directly relevant to evaluating the habitability of these exoplanets. A magnetic field, for example, is thought to be important for habitability because it shields a planet's atmosphere from erosion by stellar winds. A planet without a magnetic field loses its atmosphere much more quickly than one with a magnetic field. Mars, which has no global magnetic field, has lost most of its atmosphere over geological time. Understanding how Neptune's unusual tilted offset magnetic field works, understanding the ice giant dynamo mechanism, tells us something about whether sub-Neptune exoplanets are likely to have magnetic fields and what those fields might look like. This has direct relevance to evaluating whether sub-Neptune planets in habitable zones could retain atmospheres long enough to be habitable. Neptune's atmospheric composition and chemistry also informs models of exoplanet atmospheres. When we observe the atmospheres of sub-Neptune exoplanets using transmission spectroscopy, measuring how starlight filters through a planet's atmosphere as it passes in front of its star, we're looking for signatures of molecules like water vapor, methane, carbon dioxide, and ammonia. Interpreting those observations requires models of how these molecules behave in the temperature and pressure conditions of ice giant atmospheres. Those models are informed by what we've learned from studying Neptune. The better we understand Neptune's atmospheric chemistry, the better we can interpret observations of exoplanet atmospheres. Neptune is not separate from the search for life. It is part of it. Understanding Neptune helps us understand what kinds of environments in the universe might be capable of supporting life, and what those environments look like from the outside. This is a point that is sometimes lost when people frame the Neptune exploration debate as a choice between exciting things like looking for life on Mars or Enceladus versus studying a cold, distant, lifeless planet at the edge of the solar system. Neptune is not separate from the story of life in the universe, it is embedded in it. Chapter 12. What Neptune teaches us about being small. I want to take a moment before we wrap up and do something that science videos don't do often enough. I want to just sit with the scale for a second. Not in a facts and figures way, but in a genuinely contemplative way. Neptune is 4.5 billion kilometers from the Sun. The light that left the Sun this morning will not reach Neptune until this afternoon. When Voyager 2 was flying past Neptune in 1989, the radio signals it was sending back, travelling at the speed of light, took 4 hours to reach the antennas on Earth. The engineers who were monitoring the spacecraft were seeing what Voyager was doing 4 hours after it happened. They were managing a spacecraft encounter in the past. They were living 4 hours behind. That distance is almost impossible to hold in your head meaningfully. We use the words 4.5 billion kilometers, and we process them as a large number, and then we move on. But try for a moment to actually feel that distance. If you drove a car at highway speed, non-stop, 24 hours a day, Without stopping for gas or sleep or food, it would take you approximately 5,000 years to reach Neptune. The entire span of recorded human history, every civilization, every empire, every war and revolution and work of art and scientific discovery would not be enough time. You would need to go back to before the pyramids were built and drive continuously until now, and you still wouldn't be there. And yet we found it. We found it with mathematics, before we could even directly see it clearly. We sent a spacecraft there. That spacecraft, built by human hands with human knowledge, travelled those 4.5 billion kilometres and returned to us images of a world we had never seen, measurements of a magnetic field we had never imagined, evidence of geological activity we had never predicted. And the people who planned that mission, who designed those instruments, who calculated those trajectories, are human beings. The same kind of creatures who also forget where they put their keys and argue about parking spaces and procrastinate on their taxes. There is something in this that I think deserves more attention than it gets. The exploration of Neptune is not separate from what it means to be human. It is an expression of what it means to be human. The impulse to reach out into the darkness and understand what is there. To refuse to accept ignorance about the universe we live in. To insist on knowing. To send a machine 4 hours at the speed of light just to find out what a distant world looks like. That impulse is one of the most distinctively human things there is. And the fact that we haven't gone back in 35 years is also very human. We get distracted, we have other priorities, we are constrained by money and politics and institutional inertia, and the sheer difficulty of sustaining a long-term commitment to something that doesn't pay off for decades. We're not always our best selves. Neptune has been waiting for us to come back, and we have been busy with other things. But Neptune is patient, in the way that 4.5 billion-year-old planets are patient. It will still be there when we get around to it. It will still be doing its extraordinary, baffling, inexplicable things, its supersonic winds, its disappearing storms, its diamond rain, its backwards moon, its broken magnetic field. It will still be waiting to be understood. And the fact that it is not yet understood, the fact that there are genuine, important, consequential things about Neptune that we simply do not know, that our best models cannot explain, that no existing dataset can resolve, is not a failure. It is an invitation, an open door, a planet-sized question mark sitting at the edge of the solar system, emitting heat from a source we can't fully explain, generating winds faster than sound by a mechanism we don't completely understand, surrounded by a ring system with arcs that physics says shouldn't persist, orbited by a moon that theoretically shouldn't be there. Science is fundamentally about that feeling. The feeling of staring at something that doesn't make sense yet, knowing that if you look carefully enough and think hard enough, and are patient enough, it will eventually reveal its logic. And Neptune is full of that feeling. Neptune is one of the richest repositories of scientific mystery in the accessible universe. Conclusion: the wildest giant is still waiting. Let me bring this all together. Neptune was discovered in 1846, not by accident, not by luck, but by the sheer power of mathematics applied to an observational anomaly. Two people, working independently on opposite sides of the English Channel, pointed their calculations at the sky and said, "There is something there, and it is here." And they were right, within 1 degree. This was one of the most profound demonstrations in the history of science that the universe obeys mathematical laws, and that those laws are discoverable by human minds. Neptune is classified as an ice giant, the most distant planet in our solar system. Its interior is likely dominated by exotic high-pressure fluid ices, water, methane, and ammonia, in states of matter that don't exist naturally on Earth's surface, potentially including a layer of superionic water, and, in deeper regions, a continuous rain of diamond crystals falling through the mantle toward a diamond-enriched core. It generates 2.6 times more heat than it receives from the Sun from an internal source that we have not fully characterized. Its atmosphere is the most violently dynamic in the solar system. Wind speeds reach 2,100 km per hour, nearly twice the speed of sound, driven by internal heat rather than solar energy, by a mechanism we do not fully understand. Giant storm systems the size of entire planets appear and disappear on timescales of years, defying our models of how large planetary vortices should behave. The seasonal cycle is 40 years long per season, and we have not yet observed a full Neptunian year with modern instruments. Its magnetic field is tilted 47 degrees from its rotation axis and offset from the planet's centre by more than half the planet's radius, a configuration unlike anything seen on the gas giants, almost certainly reflecting a fundamentally different dynamo mechanism operating in the exotic icy mantle rather than in a metallic core. The origin of this unusual magnetic architecture is an open problem in planetary physics, with implications for understanding the magnetic environments of the most common type of planet in the galaxy. Its ring system, discovered definitively by Voyager 2 in 1989, contains the extraordinary Adams ring arcs, concentrated clumps of ring material that persist despite the physical expectation that they should spread out and dissipate, maintained by a delicate gravitational resonance with the moon Galatea that is still not fully understood in all its details. Its largest moon, Triton, is a captured Kuiper Belt object, a world that was born elsewhere in the solar system and was violently incorporated into the Neptune system through gravitational capture. Triton orbits backwards. It is geologically active, with nitrogen geysers erupting from its surface observed by Voyager. Its surface is young, continuously reshaped by internal geological processes. Its interior may contain a liquid water ocean maintained by tidal heating. And it is on a slowly decaying orbit that will end in about 3.6 billion years in its catastrophic destruction by Neptune's tidal forces. Neptune itself migrated to its current position from a much closer orbit during a dramatic period of dynamical instability in the early solar system. A migration that scattered the primordial Kuiper Belt may have triggered the late heavy bombardment that peppered the inner planets with impacts, and may have played a role in delivering water and organic compounds to the early Earth. And all of this extraordinary scientific richness has been visited by exactly one spacecraft for approximately 6 hours of close observation 35 years ago. We have not gone back, but the most important thing I want you to take away from this video is not a fact about Neptune. It is a feeling. It is the feeling that the universe is genuinely, inexhaustibly strange, that even in our own solar system, the 8 planets and their moons and rings and asteroid belts, the system we have been observing for thousands of years, there are worlds that still hold secrets we cannot explain, worlds that our best models and our best mathematics cannot fully account for, worlds that are doing things right now as you watch this video that no human being yet understands. Neptune is one of those worlds. Neptune is the wildest giant in space, and the wildest thing about it might be how little we know. We will go back, not soon enough probably, not as soon as the science warrants, but eventually humanity will send a spacecraft to orbit Neptune, to fly close to Triton, maybe even to land on it. And when that spacecraft arrives, when, after a 12 or 15-year journey across 4.5 billion kilometers of empty space, it fires its engine and falls into orbit around that deep blue world, what it finds will almost certainly surprise us, will almost certainly challenge our models in ways we cannot predict from Earth, will almost certainly reveal that the universe is stranger and richer and more extraordinary than we currently understand. That is not a worry. That is not a problem. That is the whole point. That is what exploration is. Neptune has been waiting for 4.5 billion years. It can wait a little longer, but I hope we don't make it wait too much longer.